video on polar coordinates, okay? Let me first get to some deep questions about coordinates in general. Before, we've dealt with rectangular coordinates, meaning in the Cartesian coordinate plane, actually, René Descartes, some guy named René Descartes, some French guy a long time ago, was sitting in his room and saw a little bug on the wall. And René Descartes thought, I bet you I can model with numbers the location of that bug, the fly or whatever, ladybug, on the wall if I were to pinpoint, given some origin point, origin O, right here, I can pinpoint its location right here by saying how much did it move on this X and how much did it move on this Y. This is where rectangular coordinates got invented, because that bug's location at some X comma Y is precisely at the tip or at the edge point of a rectangle. And any point that is described in rectangular coordinates, let's say some point out here, it's got some X right here, it's got some Y. Notice these dotted rectangles that form. Therefore, whenever you have some X comma Y, some X value, Y value, describing the location of a point, we call that rectangular coordinates because it makes rectangles. Now, it's not the only way to describe the coordinates or the location of an object in the plane, in two-dimensional Euclidean space, as what us nerds would say. We can say that that bug's location actually emanates some radial distance r from the origin and some angle theta up from the x-axis. This angle theta allows us to introduce trigonometry in our discussion of determining and distinguishing coordinates. So, polar coordinates are coordinates that take in two pieces of information, a radius and an angle above the x-axis, whereas rectangular coordinates, these guys just take an x and a y. The rectangular coordinates are very linear in nature. They want to measure in the line, in the x-axis, how much do we got, and in a line on the y-axis, how much do we got. But polar coordinates say, yeah, we'll use this linear measuring property to measure just how far away directly is it from the origin, and then the other piece of information I need to know is just an angle. Why is that important? Well, we're studying trigonometry, and we're studying triangles, and triangles have angles, and now we can introduce them into the discussion. Notice now that if I forget about the whole bug, let's forget about the bug and some history about René Descartes and how it was thought of. The Cartesian coordinate system is named after René Descartes, a French polymath. And so let's go over here and talk about some random point P. P is equal to some x comma y in rectangular coordinates, correct? There's some x and some y associated with this point P, okay? But we want to talk about polar coordinates, meaning we want to establish what this distance r is and what this angle theta is. Before we can move on into our discussion between polar coordinates, we need to have a way to go from here to here. That is transformation. We need to know how to transform rectangular information into polar information and vice versa. We need to know how to do it the other way around as well. So the way we create our transformation equations in mathematics is we use trigonometry. Take a look. This right here makes a right triangle. Right here, this is a right triangle. And if we just take out the triangle and just observe it right here, this leg is x, this leg is y, this is my theta, this is my r. Let's do some trigonometry on it, okay? Cosine of theta is adjacent over hypotenuse. So when I solve for x by multiplying both sides by r, I get r cosine of theta is equal to x. Notice that doing so, now I know how to move from rectangular, which is x, to polar, which is r, and theta. Let's do sine of theta. Sine of theta is equal to y over hypotenuse, opposite over hypotenuse. And then solving for y, I get r sine of theta is equal to y by multiplying both sides by r. This right here and this right here are the x and y transformation equations. Now, we need to find a transformation equation for r. How do we relate r? Well, it's quite simple. It's the Pythagorean theorem. The Pythagoras' student's theorem states that r squared is equal to x squared plus y squared. Even an elementary school or middle school student could tell you that. And then when I take the square root of both sides, then I get r is equal to merely x squared plus y squared. And now we know how to find r. And we know how to find theta. R is very simple and explicit. Finding theta is very easy as well. If we just take the ratio of y over x, I get r sine of theta, divide by r cosine of theta. R's cancel, so I get tangent of theta is equal to y over x. I can solve for theta by taking the tangent inverse of both sides. So the tangent inverse of y over x becomes my theta. And so now I also know how to find theta, I know how to find r, and I know how to transform from rectangular to polar, or from polar to rectangular. This is part 1 of the elementary discussion of polar coordinates, where I introduced to you the transformation equations, and the motivation behind creating polar coordinates to begin with is because we want to introduce the beautiful mathematics of trigonometry in locating points, which is very, very useful, as you will see.